no translational symmetry. I will show you translational symmetry in resonant response. In crystal diffraction, the diffraction follows Bragg's law. N lambda equals 2d sine theta. Here's d, the interplanar spacing. Lambda is the wavelength. And theta is half the scattering angle, the Bragg angle. And here's n, 0, 1, 2, 3, 4, 5, 6. Sometimes the scattering factor is 0. In quasicrystal, it's completely different. N is given here, 0, 1, tau squared, tau cubed, tau to the fourth. Tau is irrational. It's aperiodic, it's anharmonic. And your first problem is, how in heaven and earth does it diffract? I'm going to show you that harmony is essential in modern physics owing to wave-particle duality, such as the solutions to the Schrödinger equation are all harmonic. Here I describe harmony in quasicrystals. Consider, Michelson and Morley falsified the ether theory. It was replaced by Einstein's law of physical laws. They are all invariant in inertial systems. Measurement, on the other hand, is relative. He derived the formula energy squared is momentum squared plus mass squared, where c is the speed of light. In simplified units, m squared can be represented as a function of e plus p times a function of e minus p, which is a function of omega plus k plus omega minus k. Omega is the angular frequency, k is the wave vector. The first bracket conserves particulate properties, energy, momentum, etc. The second responds with a normal interference wave function. Here's the particulate part, and here's the response function. What I'm going to show you is that the quasicrystal digitizes and harmonizes the periodic radiant probe, the incident probe, and it harmonizes them in the irrational solid. I'll show you in 8 steps. We'll discuss structure, indexation, Bragg's law and structure factors, the quasi-structure factor and metric, the analysis and irrational residue, the quasi-Bloch wave, digitized and harmonic, and the lattice parameter, measured, analyzed, verified, and complete. Start with the unit cell manganese at the center, surrounded by 12 aluminum atoms closely packed. The unit cell is edge-sharing, so the stoichiometry is aluminium 6 manganese. And notice this feature that normal to the 5-fold axis is a circle of 5 aluminum atoms. 2 circles of 5 aluminum atoms. We're going to see those again. And the cluster is hierarchically arranged. The unit edge width of the unit icosahedral unit cell stretches to tau squared in the icosahedral cluster, and in the supercluster, tau to the power 4, etc., etc. And here they are. Here's manganese, here's the unit cell, and here's the cluster, 2 circles of 5 atoms. And here's the supercluster, 1 circle of 5 clusters. Notice that the interplanar spacings are irregular and multiple. And here are the manganese atoms mapped for a supercluster and for a supercluster order 2. 10 unit cells in a cluster on 2 circles, 5 clusters in a supercluster on 1 circle, and in a supercluster order 2, 10 clusters in a supercluster. When we include the aluminum atoms and manganese atoms, the clusters touch, as indeed they did, especially at the contact points between 2 clusters. So we have a structure which matches the phase contrast optimum defocus image. Before we go on to calculations, we must get the indexation right. Here's a stereogram of the icosahedral structure, and normal to the principal axes are the diffraction planes. They are all three-dimensional, geometric, simple, and complete. Dimensions should not be multiplied without necessity. The harmonic rank is R4. And now I'm going to compare Bragg's law in crystals with the hierarchic diffraction in the quasi-crystal. Red rays are first order, green rays are second order. And notice that because of harmony and because of Bragg's law, the wavefront is coherent after Bragg reflection. But in the quasi-crystal, because of the multiple interplanetary spaces, the wavefront is incoherent. It shouldn't diffract at all, but it does because of the special features of the icosahedral structure. So how do we analyze it? We analyze it with structure factors because they are independent of Bragg angle theta. In the crystal, we project each atom site in a unit cell onto a selected plane normal, sum the cosine phases to get the amplitude that we saw in the first slide. In that case, it was either 1 or 0. In the quasi-crystal, we make two adjustments. Firstly, because we have multiple d-spacings, we include a coherence factor, which we're going to analyze in detail as we go along. Secondly, because our unit cell is not periodically repeating, we have to sum over the whole quasi-crystal, and we have to do it iteratively. The QSF for a supercluster order P is equal to the QSF order P minus 1 multiplied by this function of the stretching factor. And what is the answer? There is no Bragg diffraction. If there were Bragg diffraction, it would occur on the ordinate axis where CS equals 1. But when we scan CS away from the Bragg condition, the quasi-Bragg peaks pop up. They pop up at the same position for those 5 beams we started with, and they pop up at the same position for all the beams in the original data. It's a universal number. It has the value 0.894, derived here numerically. And what is CS? You can see from the formula that adjusts the lattice parameter or the reciprocal lattice parameter. It's a breathing strain, switching the diffraction on and off, like the rocking curve from crystals. And we can analyze it. By mathematical induction, you can prove that the irrational number tau to the power m is equal to this Fibonacci sequence. 0, tau, 1, tau, 1 plus tau, 1 plus 2 tau, 2 plus 3 tau, 3 plus 5 tau. And you can see from this that it has two parts, a natural part and an irrational part. And you can rationalize this by substituting for tau the irrational fraction 3/2, and then you get a natural part and an irrational residue by subtraction from the irrational order. The irrational residue forms a metric function when it's normalized by this Fibonacci sequence, which I'm going to demonstrate, and it has the extraordinary property that it is the exact inverse of the coherence factor that we derived completely independently, derived numerically. And I can illustrate. Look at the blue wave. The blue wave is a Bloch wave which is commensurate at the unit cell and commensurate at all unit cells in a crystal, but incommensurate with the geometric series in the hierarchic structure. However, if we stretch the blue wave by the metric function, we get a quasi-Bloch wave which is commensurate at all intercepts, both long range and short range. This has all the properties we need for diffraction. Notice one further feature, that count the intercepts between the cycles between intercepts 1, 2, 3, 4, 5, and notice 1, 2, 3, 5, 8, 13, 21, 34. This is the Fibonacci sequence denominator that we saw in the metric function, so we understand the metric function very well indeed. You can recombine Bloch waves to produce a lattice image, but I'm not going to say anything more about that. Let me point out that these quasi-Bloch waves have translational symmetry. They are invariant under all translations, a tau to the m. This table tells you how to calculate the quasi-lattice parameter, but I'm not going to spend time on it. I'm just going to illustrate for you what the quasi-lattice parameter is. Here's the unit cell cross-section. There are 15 identical cross-sections at various angles in the unit cell. So it's a quasi-spherical structure. And the lattice parameter has the same dimension as the diameter of aluminum as measured. And so we can sum up. The quasi-crystal metric digitizes and harmonizes the resonant response. Mathematicians do what they do, and they do what they can. They like to create and annihilate alternate universes. But in physics, we have to test, and we have to know. We have to know how harmony is essential to resonant response in quasi-crystals, as in Schrödinger's solutions.